In this video, I'm going to show you how to compute volumes of revolution using the shell method for a rotation about the x-axis. The key idea behind the shell method is that you just break up your volume into a bunch of cylindrical shells. So before we get into shell method problems, we're going to start out by finding the volume of a single cylindrical shell of radius r and length l. The result we find here will give us a good starting point when it's time to actually apply the shell method. Okay, so a cylindrical shell. What does a cylindrical shell look like? Well, it's cylindrical, which probably tells you that it just looks like a cylinder. And this is most of the idea. So let's draw a cylinder. We'll make it horizontal cylinder because that's what we'll be using for rotations about the x-axis. Okay, so here is a horizontal cylinder. But we're talking about a shell, not just a cylinder. A shell surrounds some kind of volume, so we have to carve out a bit on the inside. So let's make another cylinder on the inside here and draw it so it looks like it's running through the cylinder. So the idea here is that the cylindrical shell is really like a PVC pipe. And there's two volumes here. The first volume is the volume of the liquid that you can fill the pipe with. That's like the volume of the inner cylinder. But that's not the volume that we're interested in. We're interested in the actual volume of the region of space taken up by the pipe itself, which is the volume of the material that actually makes up the pipe. So not the inner volume, but the between volume that would correspond to the volume of the pipe. So think about taking this kind of washer here and taking those cross sections throughout the cylinder, and you'll come out on the other end right over here. It's the volume of the walls that we're interested in. The walls have a non-zero thickness, and that's the volume we want. So how do we actually compute this volume? We know what the volume looks like, but how do we actually compute it? Well, the idea here is that we do a transformation to the cylinder that preserves its volume but turns it into a shape that's easier to compute. Namely, we cut the cylinder. So let's draw some scissors up here. These are scissors cutting the cylinder, and we're cutting right along here, say. And what happens when we cut the cylinder there is that it unravels, and we get a rectangular prism. Let's just draw that out there. Alright, so it looks something like this, and there's some thickness of the walls as well. So this top is where the scissors were. The scissors were right about here, and they cut along here. And that also matches up with the bottom too. The bottom was initially attached to the top. They were both over here, but then you unraveled them and now it just hangs straight down. This colored washer here is now this side over here. Now the volume of this rectangular prism is a lot easier to compute. All we have to do is multiply the dimensions together. So let's figure out what the dimensions are. First, let's draw in the length, L. So L can be right over here. That's the length L, and then when we unravel it, that just stays as this length of the horizontal dimension, length L. And let's also call the width of the washer here, let's call that the thickness. So then that thickness, the thickness of the wall, becomes the thickness, kind of like the depth of the rectangular prism here. So this becomes the thickness here. So it remains to figure out what is this dimension here. Well, that dimension just comes from unraveling the cylindrical shell. So that's like the circumference of a circle around the shell, like here. Now we know that the shell has radius r, so the circumference is then just 2 pi times r. So that's the distance around there, the circumference. So that becomes this dimension here, 2 pi r. The volume of the cylindrical shell then just comes from multiplying all these dimensions together. So volume is just 2 pi r times L, length, then times the thickness. And this here is what we're going to use as the starting point for the shell method. So keep this formula in mind as we move on to some problems. Alright, so now let's jump into a problem that involves using the shell method to compute a volume obtained by revolving the region bounded by x equals y squared and x equals 1 in the first quadrant about the x-axis. Okay, so let's just start off by getting a sketch of this region which we're rotating around, x equals y squared and x equals 1. Why don't we draw x equals y squared first? That's just a parabola opening in the positive x direction. We can plot a few points when y is 1, say that's y is 1, x is also 1, so we'll make that equal to 1. Right over here, then when y is 0, x is 0, it's right over here. When y is negative 1, x is also equal to 1, negative 1 squared is just 1. So it's a parabola looking like this. Alright, so that's our x equals y squared, and then we've also got x equals 1, so that's just a straight line, x equals 1, right over here. There we go. And now let's shade in that region. Remember, we're only looking in the first quadrant, so we're only going to shade the part of this region that's in the first quadrant, right over here. So that is the region that we're rotating around the x-axis. So we're rotating that around this way. And maybe try to visualize this a bit. When we rotate this region around the x-axis, then we end up with a solid that looks kind of like the tip of a football, maybe. If you were to take, say, a foam football and just slice off the tip here, then that'd be your region that you get from rotating. Alright, so now let's draw this region again, but let's try to visualize what these cylindrical shells look like. So we'll still have our parabola here, and we'll have our line, x equals 1. Alright, and now we want to draw in a cylindrical shell. Alright, so cylindrical shell will be across here, this way, and it'll be revolving around this way. So we'll have a nice cylinder there, but we want to carve out an inner cylinder to create a shell. So this will be inner cylinder, there will be the wall, the pipe wall, and then that inner cylinder will go all the way through the shell, on the other side also. Now let's recall our volume formula for the volume of a cylindrical shell. We know that from the previous slide, that's just volume of shell is equal to 2 pi times the radius times the length times the thickness of that shell. And let's go ahead and look at our shell and figure out what the radius, length, and thickness are here. First of all, the radius. So the radius is just the distance from the center of that shell to the exterior of the wall here. And that's just the radius, which is equal to the y value, which our shell hits here. So that's going to be, radius is equal to the y value here. That's how high up it goes. Alright, so we've got 2 pi times y. Now how about the length? So the length of a shell, again, is just this dimension here, the horizontal dimension. So that's going to be the difference in the x endpoints of the sides of the shell. So let's label this with length, and let's also figure out what are the endpoints here. We already know that this endpoint over here, that's when x is 1. That's when x is 1 because that's the line x equals 1. Now the left endpoint, that happens to be on the parabola. And the parabola, the x coordinates are given by y squared. So this x is given by y squared. So the length is just the difference between those, 1 minus y squared. So that's what we'll put in for the length here, 1 minus y squared. And then lastly, we have the thickness. And the thickness is just the thickness of the wall of our shell. So that's just the distance here. And that distance is going to be a small change in y. So dy. That's the thickness. Okay, so thickness is dy. So that is going to be the volume of one of these shells. Infinitesimally thin shell with thickness dy. And now we're going to get the volume of the entire region by summing up all of these shells that comprise the region. So the volume of revolution is just going to be the integral of the volumes of these shells. And volume of shell is just 2 pi y times 1 minus y squared dy. And what are our bounds for our integral? Well, what does y range from in our diagram? It starts out at 0 here. We're starting out at the very bottom of the first quadrant, y is 0, and it goes up all the way until the curves intersect, and that point is just 1 there. So from 0 to 1 for y, and now we just have to go ahead and multiply this out and integrate. So let's go ahead and do that. So that's equal to integral from 0 to 1. Why don't we actually pull out the 2 pi to make this a little bit simpler? So that's equal to 2 pi times this integral from 0 to 1 of y times 1 minus y squared. Well, that's just y minus y cubed dy. And what is that equal to? Well, that's just equal to 2 pi times, let's go ahead and integrate this. Integral of y is just y squared over 2. Then minus integral of y cubed is just y to the 4th over 4. Take that at the bounds 0 and 1. Okay, so that's equal to 2 pi times the bounds at 1. So 1 squared over 2 minus 1 to the 4th over 4. And then minus 2 pi times the bounds at 0. And well, this is just 0 over 2 minus 0 over 4, so still everything times 0. Then that comes out to 2 pi times a half minus a fourth, which is equal to 2 pi. A half minus a fourth is just 2/4 minus 1/4, which is just 1/4. Okay, and then 2 pi times 1/4, go ahead and cancel the 2 with that 4, turns into a 2, so that's just pi over 2. So there we go. That is the volume of our region. Great, so we found the volume, and how about in the future, to save some work, why don't we look back at our steps and see if we can come up with a formula for the volume of revolution here. So volume of revolution is always going to be an integral of the volumes of the shells. And the volumes of the shells, when we are revolving about the x-axis, well, we'll have 2 pi. The radius will always be the y-coordinate, because that's how high up the shells go. So that's the radius of the circle at the base of the shell. So 2 pi times y. And then the length. The length is always just the horizontal distance of the shell. So that just goes between the left and right x-coordinates here. We make that a positive number by subtracting x right minus x left. So let's go ahead and write that down. X right minus x left, and then times the thickness of the shells, and thickness is always dy when we are rotating around the x-axis. Okay, so we take those volumes of the shells and we integrate over the region that we're rotating. We integrate over all the y values. We'll just say for y ranging from a to b. In this case, a and b were just 0 and 1. 0 and 1 here, but we might have different y values in future problems. But this is going to be our formula going forward. Volume equals integral a to b 2 pi y x right minus x left dy. Okay, so let's do one more problem. We want to use the shell method to compute the volume obtained by revolving the region bounded by x equals y squared, that same parabola, and x equals 2y minus y squared about the x-axis. All right, 2 minus y squared, that's a backwards parabola, and it's intersecting here and here, and we want to take that region right over here and rotate it around the x-axis. Okay, so let's start where we left off last time with our formula. The volume is just the integral from a to b of 2 pi times the radius, which is y, then times the length, which is the difference in x endpoints, so x right minus x left, times dy, which is the thickness of our shells. To keep a good visual, why don't we actually draw in one of those shells here? So let's go ahead and draw that. Here will be one of the shells, and it's rotating around this way. Make a little cylinder, carve out a bit on the inside to create a shell, and there we go. There is our shell. So now let's fill in what we have in this integral. So this is just the integral. What are the endpoints? What's a and b? Well, a is the lower endpoint. That's going to be right over here where the region starts. There is 0. And then b is the upper endpoint. So that's where the region ends, which is the y-coordinate right over here, which is just 1. So from 0 to 1 of 2 pi, then times y, and then x right and x left. We want to figure out what those are in terms of constants or y. So let's go ahead and dot those here, here, and here. So x right is over here, and that x-coordinate lies on this blue curve, x equals 2y minus y squared. So x right equals 2y minus y squared. Let's go ahead and plug that in, 2y minus y squared, and then minus x left. X left is just this other point here, right there. That lies on the red curve, which is just x equals y squared. So x left equals y squared. Great, so just minus y squared over here, and that's all dy. Great, so now our integral is all in terms of y, and we're ready to go ahead and compute it. So let's go ahead and do that. So this becomes 2 pi goes to the outside, 2 pi integral from 0 to 1, and then we can multiply the y through, so 2y squared, and then this is minus 2y, then times y, so minus 2y cubed dy. Alright, time to integrate this. Why don't we also factor out another 2 here? Since we have 2 in both of these terms, we can just pull out another 2, make this 4 pi integral from 0 to 1 of y squared minus y cubed dy, and now we'll go ahead and integrate that. So 4 pi y squared, the integral of that is just y cubed over 3, then minus integral of y cubed is just y to the 4th over 4. Alright, the bounds are 0 and 1 for that, so then that comes out to, well, we wrote it over here, 4 pi times bounds at 1, that's just 1 cubed over 3, so just 1/3, minus 1 cubed over 4, so 1/4, and then minus 4 pi, the other bounds, plug in 0 for y here, both terms go to 0, so just 0, and then that comes out to 4 pi times 1/3 minus the 4th, well that's just 4/12 minus 3/12, so 1/12, and then that other term goes away because it's just times 0. So 4 pi times 1/12 equals, cancel out a 4, cancel the 12 to get 3, then we just have pi over 3. There we go, so that's our volume of revolution. Now before we end, let's talk about why we use this shell method. You might say, well, this seems much more complicated than the disk or washer method, so why can't we use that? Why do we have to use the shell method? And the answer is that in order to use the washer or disk method, you need to find y as a function of x for both of the curves. Alright, so given our curves here, x equals y squared and x equals 2y minus y squared, x equals y squared, you could find y as a function of x for that. You can just take the square root, but how about x equals 2y minus y squared? That's a lot harder to solve for y in terms of x. I guess you could use the quadratic formula here, and then you could get y as a function of x. It would be kind of ugly, kind of time consuming, Also, what if this were, say, x equals 2y minus y cubed? Then you couldn't use the quadratic formula. You'd have to figure out a different way of doing it. So that'd be very, very, very hard using the disk or the washer method. But using the shell method, you can just substitute in your x right and x left in terms of y. Just keep everything in terms of y. Don't worry about solving for y in terms of x. Just keep x in terms of y, and you can just perform this entire integral with respect to y. So shell method is always really useful when you have bounds that express x as some function of y that would be difficult to solve for y as a function of x. In this video, we focused on using the shell method for rotations around the x-axis. However, in the future, we'll also see how to use the shell method for rotations around other horizontal lines.